Okay. Hi everybody. My name is Frédéric Wautelet. I'm a system engineer and I'm in charge of the management of the HPC infrastructure at the University of Namur. And I'm very pleased to show you a quick overview of what we are doing with EasyBuild at CÉCI. Donc, first of all, what is CÉCI? CÉCI stands for the Consortium des équipements de calcul intensif. It's a consortium of high performance computing center of the 5 universities in the French part of Belgium. So Mons, UC Louvain, University of Namur, Liège et ULB. And the CÉCI is funded by the scientific research and the Walloon region. And all the facilities of the consortium des équipements de calcul intensif are accessible by all the researchers of the member universities. So there is about 450 active users on CÉCI, and you see here a quick overview of the field of application that run on the CÉCI clusters. There is 5 clusters, one in each institution, and the CÉCI cluster in fact be designed to accommodate a large diversity of workload and needs for the researcher. And for example, the 2 Hercules and Dragon 1 has been designed to cope with sequential jobs, and the 3 other ones are designed to run parallel jobs. And currently the CÉCI infrastructure is being upgraded. Le Maître 3 has been upgraded last year, and this year we will upgrade Hercules and Dragon. You will see that for Namur we will install AMD EPIC processor, and in Mons they will install Skylake as well as several nodes with NVIDIA Tesla V100s. The CÉCI also provide a common storage. This common storage is visible for all the front-end and the compute nodes on all the CÉCI clusters. In fact, each cluster has its own gateway to access this distributed storage, and the technology behind this storage is based on GPFS, renamed Spectrum Storage by IBM. And the main purpose of this storage is to allow the user to transfer data between the cluster, but also to store all the scientific application, part of the scientific application we deploy at the CÉCI. So, in terms of the build of the scientific application, there are several objectives. The first one is to allow the reproducibility of the science by allowing the user to reuse older version of the software. Also, we aim to provide optimized version of all the software we install. We try to version all the recipes as well as the infrastructure code we use, and we try we want to also to install all the scientific application in an automatic way. Also, we would like to have a system that is flexible enough to cope with new hardware, new node architecture, and also to cope with the new needs of the user. There are different challenges. The first one is that the CÉCI is the multi-site consortium with 5 HPC teams with an heterogeneous hardware with several architecture, and each team has its own workflow, its own hardware, etc. Also, we plan to set up a Slump federation that allows the user to submit a job from one front-end to any compute nodes on the CÉCI. And also, we have a bunch of commercial applications, such as MATLAB, Gaussian, VASP, and we must take account of this of the license limitation and restriction. For the design choice of the setup, the first one is that all the software installed at CÉCI is optimized for the architecture of the nodes. We use compilation farms to compile other application, or the compilation is done directly on the compute nodes using slurm -- jobs. Also, we generate packages using FPM. These packages can also be installed on the distributed storage. And the use of packages allows us to uninstall cleanly all applications without breaking something. And all the packages generated are archived, so we can downgrade application if needed. Also, as already said, a great part of the application are installed on the distributed storage. And of course, we use EasyBuild to install almost all the application at CÉCI. In terms of the directory layout, you can see here an example of the directory layout currently on the distributed storage. The first thing to describe is that because we have commercial application with restrictive licenses, we need to install application locally on each clusters to avoid problems with the legal teams or something like that. And the rules here, freely available application, mainly open source software, are installed on the distributed storage, with the exception of the Intel Java and Portland compiler, and all the other restricted software, all the commercial software or software that needs registration are installed locally and are only available locally on each site. In terms of dependency, application installed locally can depend on an applications installed on the distributed storage, but not the other way around. Okay, let's take a look at the first level here. We can go closer. There is a naming convention here. The first part identifies the distribution with the version, and in fact it's based on the Ansible fact, as the Ansible is the tool we use to deploy automatically the nodes, but also the compilation farms as well. So for example, you can have a Red Hat 7, Debian 9, or something like that. The middle part is in fact the identification of the processor in terms of processor family, model, and stepping. And the last one is the interconnect. So for example, currently on the common storage, the following architecture are installed. We support with only pass, InfiniBand, etc. None is for gigabit connected cluster. There is a special case, is the noarch. It's for architecture independent softwares. Typically at CÉCI, it's mainly to store databases such like NCBI Blast or SweetSpot. And the second level, we use the installation framework. You see that currently we use only two installation framework, the EasyBuild and manual installation. Manual installation is used for application that we don't have yet recipes to install it, or for example to install Blast databases, etc. And we support EasyBuild, but the organization, so the directory layout, is set up to accommodate another installation framework if needed. The level 3 is based on EasyBuild release. So in each subtree here, you have all the module software compiled with the same version of the toolchain. And so, for example, here you are all the application compiled with 2070B FOSS and Intel toolchain. There is a default release set CC wide, so all the clusters have the same default release. This default release is updated once a year, and each release here are independent of the another. Okay, the user have always access to the other release and can test future release. And there is a special case for what we call TIS modules. It's for toolchain independent software. It's mainly designed for applications that need a specific version of a compiler. For example, Gaussian is only compiled with a specific version of the Portland compiler. Also the case for software bundled as binaries, such like MATLAB, Mathematica, Crystal, etc. And we upgrade this module every 3 or 4 years. As the EasyBuild release, the older release are always available, and the future release are always can be used as beta. So it is the view from the storage on the nodes. We mount noarch, and depending of the architecture of the node, we mount the correct subtree. This means that on every node, the path to a certain application is the same, but it's point to an optimized version of the cluster, of the application. Sorry. So it allows us to, if it is possible, to run parallel application on different nodes with different architecture with the same path. You know that several users love to hardcode paths in their submit script. So in this case, it's also always the same paths on every node for the application. As far as the build procedure is concerned, there is no common workflow between all the CÉCI sites for the moment. For example, on one side, the build is directly done on the HPC nodes using EasyBuild -- jobs, or it is a case on Unamur. We set up a compilation farm with a virtual machine. Each virtual machine emulates all the architecture present on the HPC cluster. At Unamur, we have 4 different architectures: 2 in production, 1 for the tests cluster, and 1 for the cluster for the students. And so all the compilation is done in parallel, and on each machine emulate the correct architecture. Then we generate RPM packages. RPM packages are archived, then installed on the common storage or the local storage, depending of the license. And we keep all the RPM. If we need to upgrade one software, we increase the version of the RPM, so we keep all the version of a build in case we have to downgrade softwares. So at Unamur here, we are 1 build node virtual machine per architecture and 1 install node per architecture. For the user point of view, we plan to set up LMOD 7 for all the CÉCI clusters. Currently we only support a minimal number of toolchain, namely Sophos and Intel, as well the Portland compiler needed to compile Gaussian. And we use the default EasyBuild naming scheme. There is no plan to use another naming scheme for the moment. And all the users have access to meta module. I will show you shortly after how to use it. So the principle is to avoid the module available to list a big list, big pile of modules. So when we run a module available on the cluster, you only see meta modules, the TIS modules, and the packages built with the default release. If the user wants to have access to an older release or a future release, he has to run the one meta modules corresponding to the release he wants, and then the default release is unloaded, and the module available only show the older release in this case. So the user can change between release, and module spider always shows all the module available in every release and every version and release of this. So the user know which meta module he need to load to access specific version of the application. It's quite important to allow the user to use all the version of the application, and normally the older version are freezed, so we don't change anything, so the user can redo his simulation if needed. In terms of the future works, we plan to set up a generic build based on a generic architecture. So it's just a way to provide non-optimized build. For example, if we set up a new nodes with a new architecture, so the optimized when the optimized build are not yet available, and it is also useful to provide to the user packages to be installed on their local workstation. At Unamur, there is the user want to have the same software installed on the workstation than on the HPC cluster. Also, for future release, we plan to enable the airpath linking, and the work is almost done. We plan to automatically update documentation after every build, so the user we have on the web page all the table with that tell him on which cluster you can find which version of an application. So as a conclusion, so at CÉCI we provide optimized build for all the architecture on the system. We allow the user to load older version. We give access to future release. The user, for this case, the user just have to load a meta module, and we support special case for application that don't depends of specific toolchain. And thank you. Any question?
Thanks for your talk. Could you put back your slide on with the module avail screenshot?
Yeah.
Yes. I'm just wondering, because you use the flat naming scheme,
yeah,
but it seems you work on the software hierarchy. So
no. It's only based on release. So each release is independent, and when you use, for example, here module load release 2006B, you switch the release, but it's not hierarchical. So it's just based on the release. Yes, yeah.
So it actually is hierarchical. You just don't know.
Yeah.
So you only have one level in the hierarchy, which is a toolchain.
Sort of. Yeah.
And when you're loading a different release, what LMOD sees is a change in the module path. So it knows it has to reload all the modules or do a change in module avail. It actually is a hierarchy.
Yeah, sort of.
But it's probably not managed through EasyBuild. They're doing it
No.
Yeah. Okay.
No, not at all. Yeah, not at all.
Yeah, same as they have in Ulic with build stages. Yeah,
yeah, exactly.
More questions?
Very nice talk and very impressive. I have two questions, actually, brief ones. One is, why do you keep your license-restricted software on different file systems? Why don't you protect them just with ACLs, for instance?
Yes, there is some ACL that we use group permission or Unix permission to to block the user for using licenses restricted software, and these ACL are per site. There is no global ACL. So each HPC team has its own ACL to allow user to use commercial application on each site. For example, at Unami we have MATLAB installation, and MATLAB is only available for the local user.
Yeah, I was wondering because on our side we had the idea, like to share with you, that we have a module which is available for every user. Every user can load the module but can't execute this respective software, because then the module just shows an information upon loading that the software is restricted, and in the case of, let's say, NAMD, a user has to print out the license, send it to us, and then we enable it. And it's just less work. That's why I'm asking. Also, the second question, you compile on VMs, and I'm wondering, that's kind of dangerous, because then you have to maintain two software trunks locally on your actual hardware, and it always has to be in sync with the respective VMs, and whether that is actually necessary, because in this case we compile with -jobs on our machine, and if it fails, we know if it's failing due to the missing system library, then perhaps the node wasn't installed correctly, and or we made a mistake, and then we see it immediately.
So the VMs used in the build farm are the exact mirror in terms of installation that the production nodes. So, and because we use Ansible and packages, if we can rebuild build nodes, by just reinstalling all the RPM. If we break something, we can go back and reinstall from a specific checkpoint here.
Okay, thanks.
Welcome. Okay, thank you again.
Okay, so hello everybody. My name is Marsella, and I'm talking to present the CSCS site update. CSCS is the Swiss National Supercomputing Center located in Lugano in Switzerland. And the talk is based on the information provided by my colleagues Theophilos and Guilherme as well for the scientific computing support and compute and data services support groups at CSCS. So we will talk about the usage of EasyBuild at CSCS, the timeline of this usage, and the use cases that we have on two production systems, so that are called Cache and ESHA, and they are used by the national Meteo service in Switzerland, Meteo Suisse. And then the main production system, the usage of EasyBuild on the main production system, which is called PitStain, and it's a Cray XC system. Then we will talk about the usage of Jenkins in order to deploy the CSCS software stack using pull request integrations in GitHub and the use of pipelines with Jenkins. And then the final remarks with some future plans in order to adapt EasyBuild in our use cases. So this is a timeline of the usage of EasyBuild at CSCS. It started in 2015. Then with the help of Kenneth and Peter, it went to providing Cray software stacks as well, Cray toolchains as well on the system in collaboration with Guilherme. And over the years it increased, and now it is fully deployed. After the end of 2016, when we had a major upgrade, we deployed all the software stack using EasyBuild. So with few exceptions in some systems like the Meteor Swiss system for software that is somehow quite specific, and still we are working on deploying that within EasyBuild. There is also the need to convince some users about the usage of EasyBuild once you actually deploy some recipes. And in our repository, the number of pull requests for new recipes is now over 1,000. So it is widely used also by our users. Now, the HPC systems that we have at CSCS are listed here. So on the top, you have PitStain, which is the main production system, which consists on two types of architectures. One is a Haswell processor node with a Pascal GPU. The second type, which is called Cray XC50. The second architecture, called XC40, Cray XC40, consists of two sockets with Broadwell processors. Other systems are listed here. I mentioned already the Meteor Swiss systems, Escha and Cache, which are a Cray CS Storm system with multiple GPU on a single node. And then we have here listed two, let's call them general purpose system, Leone, which is a large memory system dedicated to a company, and Fullen, which is a virtual system built with OpenStack that is based on an Intel Broadwell and Skylake architectures for Skylake for FAT nodes that come also with GPU nodes as well. And for the moment, I think that Fullen is our test bed, let's say, for using generic tool chains, because in the Cray system we were limited to actually using the Cray tool chains most of the times. We played a bit on the Meteor Swiss system with the GMWolf tool chain, but now Fullen is the one using the standard Intel and GMWolf tool chain. We use GMWolf because for our MPI test, MVAPIC performed better with respect to OpenMPI, so that's why we were sticking to that. This is the architecture description of this of the Meteor Swiss system. As I said, it's a Cray CS Storm system which has two sockets with 12 cores processor, Haswell processor, and 8 NVIDIA Tesla GPUs. Now, the EasyBuild software stack was deployed initially by Guilherme in production in 2015, and initially we were forced to build also basic things like the GCC compilers, because the initially provided compiler by Cray was not employ correctly the vectorization as it was supposed to. PitStain, the main production system, is an Intel Xeon, is based on Intel Haswell processor and Pascal GPU on the XC50 nodes, and the XC40 compute nodes, as I mentioned before, has Broadwell processors. At the moment, we are improving a bit, so the numbers might change a little bit in terms of total scratch capacity, and for the rest is more or less the same. So PitStain, which, as I mentioned, was it underwent a major upgrade at the end of 2016, after which we fully deployed the software stack with EasyBuild. Is now in the top 500. Is now number 5 in the top 500. So still the fastest in Europe, and number 18 in the Green 500. It was Yeah, this is according to the November 2018 list after the supercomputing. And it mentions the Cray XC50 partition. It refers to the Cray XC50 partition only. Now, according to the in terms of software that we release on the main production system, we have on the left software that is based on recipes already available on the EasyBuild repository that you can find on the EasyBuilders GitHub of UGANT. The Python recipe here is actually based on Cray Python, so it's not exactly the stock EasyBuild recipe. We do that because Cray already provides 2 Python modules, and Cray separates Python 2 and Python 3. So we also follow this separation. So we will still continue separating Python 2 and Python 3. And this is just to avoid simply duplicating things that are already present, like NumPy, SciPy are already present in the basic installation provided. So we will stick to that. On other systems, we use the standard EasyBuild way of building building Python. Then Wharf, CP2K, and Gromax, Boost, GSL. Well, CP2K actually and Gromax, I think for Gromax we use a custom easy block that was provided by Victor. I don't know if it has been pushed back. Okay, yeah. For CP2K, yeah, I remember I had some discussion with Kenneth about CP2K as well. I think we still use a custom easy config just because it is a bit more flexible in terms of, sometimes we need some modifications requested by users because users are not satisfied with a single installation. They always want to modify that a bit, and in order to let them modify that, because we have custom easy configs modified by users, it's easier instead than modifying each time the easy block just to provide them some modified easy config, because each of them, CP2K is a software that is currently always updated from the SVN, and so they still wanted to rebuild, and sometimes they really need some custom features, so it's really difficult to stick to a standard version. And in terms of usage, here you see on the right side the Xold statistics on the system. Actually, CP2K and Gromax are widely used, some of the most used software at CSCS. User code means that we actually cannot identify that, so it's something that maybe it's compiled directly by the user. It's some known code maybe, but doesn't stick into our name frame of executable or module frame, so we cannot identify that immediately, and it needs some further inspection. We also have software like Quantum Espresso, VASP that are already built using EasyBuild as well. AINS is a material science software. I don't think we have a recipe for that. Usually, these users tend to build their own version anyway. Also, users of Quantum Espresso, VASP, CP2K, as I mentioned, they want to rebuild anyway. So we provide a module. We use the standard TCL module framework, but they generally tend to use their own build. So what we provide for them is anyway a system in order to modify the recipes that we actually build for them. So user, when they ask something new about modification of an existing software that we provide or some new software, we provide them with a modified easy config file. So we give them access to our GitHub repository. We point them to our local EasyBuild installation and to the documentation on our user portal, where we actually mention how to compile the code in general on our systems, and in particular, how to build within the EasyBuild framework. So the local EasyBuild framework that uses a module in order to load the environment of EasyBuild, and then users can use their own recipe or our recipes in order to rebuild the software that we support. And this has been working so far more than a year, so I think it's pretty stable. In terms of our software deployment that is based on Jenkins, I'm now going to describe a bit how this is made on our GitHub repository, because we also use that in order to deploy the standard software stack plus testing new recipes. So Jenkins is the basic tool that we use as a continuous integration tool for testing new recipes and to deploy the software stack of the packages that we maintain and support with our easy config and easy block files in the EasyBuild framework. So we have then 3 different main projects. The testing project to test to test the pull requests, the software coming, the recipes coming with a pull request to our repository. The production project, which continuously build the software according to the software list that we support. And then a regression project on Jenkins that is meant to thoroughly test from scratch every week the build of our software stack in order to check, for instance, download links and compatibility with updates and modifications on the system. Recently, we have moved on pipelines, which means high flexibility in order to perform in parallel the activities within the Jenkins tool. And each project has a separate Jenkins file which contains the configuration of the project and its version control, so every modification is tracked. And then you can easily write the continuous integration tool in parallel in order to better exploit the resources that we have. In order to submit a pull request to our production repository, these are the rules that we advertise on the GitHub page. So it's something, let's say, common sense plus some slight customization due to our architectures, GPU, non-GPU, and names of the systems. I think not so many users are submitting pull requests, but I'm pretty sure that many users, at least I know that many users are actually using their own custom files. So I think it's more or less the same as it happens for EasyBuild in general. So users tend to modify the EasyConfig file, but sometimes due to time restraints, maybe they do not contribute back. And so this is an example showing how it works. Let's say, for instance, here Dane GPU means the architecture with the GPU accelerator. You are submitting a pull request for Cafe2, which is a data science software. So a new EasyConfig file that then, after the pull request is submitted, gets to the CI and goes to the Dane GPU machine. So the architecture labeled as Dane GPU and you see on the right side how the Blue Ocean interface of Jenkins is dealing with that in pipeline. So in case you had multiple entries here, like Dane GPU or DOM NC, like multicore for another system name, then you would see multiple dots on the right side, like in this case. So here Dane only means all the possible architecture on this system, and then you see there are 2 different architectures and the 2 dots, the 2 green dots that you see over there. And for the regression test that I mentioned, so that weekly tests all the recipes that we have in our software stack in order to ensure backward compatibility with modifications that happen over the time in the systems. You can see that all the systems are built, and here it was a very lucky case, all green. Anyway, it's quite, let's say, it's quite useful to have this interface. It's quite flexible, the Blue Ocean interface and the pipeline on top of that. Now, to conclude with the final remarks, we have been testing lately to build EasyBuild recipes within Docker containers. This is the reason for that is to have reproducible builds of legacy software stacks, so outdated software maybe that cannot build no more on recent updates of operating systems. And then it's also due to resistance to change from users. So they are used to a certain software that maybe builds only on, I don't know, Red Hat 6. And that's the reason to use a container. Successful attempts so far. So CentOS 7.x, Red Hat with the caveat that you need to subscribe in order to use the Yum package manager, because otherwise you need to download yourself all the packages and it's a bit annoying. Because of course the containers in general do not come with what you use generally if you install yourself. So I try with Ubuntu and it's much easier, although it's less useful because we don't have that in production, but just for testing. And the Cray programming environment as well. So in Guillermo's group they tested that as well, producing, but that can only be used on a Cray system with the license for the software. So required steps, as I mentioned, you need to manage yourself, of course, all the dependencies in order to fully start with EasyBuild, like Python, Lmod, compilers, like GNU Intel, and then you need to create users and to deploy the Docker image to the users in order to let them access the image that you have produced. That is still work in progress, but it's probably one of the major things that we will have to do in the near future. Then moving to EasyBuild, so officially at an HPC site takes some time, as you also have mentioned before, Kenneth. So learning curve and resistance to change. In this case, it's not resistance of users, but resistance of the management, which is even stronger. So, and then easy configs versus easy blocks. So the advantage of easy blocks, they are reusable, so it's great for stable software, but there is a overhead if you have, let's say, bleeding edge software, something coming new and needing some, let's say, workaround in order to be installed. The reproducibility then, if you, how to keep track of changes, probably if you need to hack the installation, then it's a bit difficult because you suppose that you need to upload a, say, a pull request every time. At a certain point, there is a trade-off between having a local EasyBuild, as you said. If you have more than 5, probably it's too many. But sometimes it's really difficult in order to modify continuously and be accepted in a pull request. On the other hand, the easy configs, of course, let's say, they provide the advantage of being self-contained. So these are 3 pluses, but on the other hand, of course, it duplicates a lot of things because, of course, you need to copy and paste all the time within, but you can modify that easily. Then wish list, I think there is already an ongoing discussion, as far as I know, between Alan and Victor about a new command line option for allowing a try dependency version, including so dependency as well to be updated, but with version. Still work in progress. And then I think Guilherme mentioned to have an extended dry run with some more information in terms of logs, command lines. So each command line, maybe separate log for each command line. Then backup of custom easy blocks to ensure that builds are reproducible. That
What do you mean with the second thing exactly? You want to have a separate log file for each command that EasyBuild runs?
in the extended dry run.
Yeah.
Yeah.
So it is actually, when you run a build, actually, it would be nice to have a separate log only with the commands that you ran, so that you can easily copy and paste. And because right now in the logs you have output, you have what EasyBuild does and the output mix. So you need to go and pick the things that you need. And on the extended dry run, it's not exactly what the EasyBuild runs, right? You cannot copy and paste 100% sure. So if you had a log with only the actual commands that EasyBuild issued during the build, someone could just take that, copy and paste, and run on the terminal for debugging or reusing the recipe.
This has come up before, so people want to have. I think that's what you mean. Have EasyBuild dump a shell script that basically, if you just run the shell script, does what EasyBuild does. It's possible, but it's not very trivial. So there's more to just running commands. EasyBuild is changing directories, is applying patch files. Most of that stuff is not done with shell commands, but it's with Python stuff. So you would have to have. Yeah, actually there is already a wrapper for changing directories. There's dedicated functions. You can make that spit out the corresponding CD command, but to get it 100% right, it's probably very difficult, but make it work in 90% of the cases, it's probably fairly doable. Yeah. And what dry run or what extended dry run already provides now is you can copy paste all the commands it does to set up the environment. That's done in such a syntax. You can just select it, copy paste, drop it in a shell, and it will drop you in the environment, the same environment that EasyBuild does. But for when it works. Yeah, that's a special case. Yeah, it may be more complex there because there's module swap stuff that happens there, a bit of magic. Yeah. maybe open an issue on this with some more details, and then we know exactly what you're after.
Just a comment on the next point there, the backup of custom easy blocks, that's implemented now. So basically there's in an installation directory, in this reprod directory, there's the easy configs, but also the easy blocks and patch files, and there's more in there basically. I can't remember everything, but it should catch everything, I think. Well, maybe there's yeah, it catches the hooks as well. So it should catch everything to be able to reproduce. But maybe there's something we missed, I don't know.
Okay. Yeah, and then about external modules, something that I actually also ran into sometimes. So improve some error reporting for missing modules, and then having versionless entries in the metadata file when you use external modules. That it might be, let's say, error prone sometimes, but it's much easier because then you don't have to duplicate entries all the time in the metadata file. But of course, you need to take care, because as for the skip sanity check, you need to know how to use that, of course, at your own risk. So latest news, we deployed an HPC OpenStack cluster, Fullen, the one that I mentioned before, with EasyBuild, mainly using GMWolf. I also tried a bit with Intel, but I had to invent a new custom toolchain like Intel with Mvapit, so IMVMKL, something like that, which it's difficult to pronounce as well. And so far, it has not been giving good performance. But anyway, this is a problem of Intel, not of EasyBuild. The deployment was fine. And in terms of useful links, so on top, the EasyBuild user documentation that we provide at CSCS, plus the CSCS EasyBuild repositories on GitHub with custom easy configs and easy blocks, and at the bottom, the repos that are mirrored anyway under the easy builders maintained by UGent. So easy builder/CSCS, and then you have the common tree structure. And thank you for your attention. That's it.
I have a small question, not exactly related to EasyBuild, but to Xalt, just curiosity. When did you start using Xalt?
Well, we used that already, well, before it was ALT-D, then it became Xalt, so for a long time. After the latest upgrade of PitStank in 2016, I think we migrated to Xalt. And Victor and my colleague Jean-Guillaume were always fine-tuning that in order to have a better report, because as you know, you need to match the names of the actual modules. Well, when they use our provided modules, it's quite easy, I think, and the libraries. When they use custom software, Victor and JG managed to have a mapping of the names of the executables in order to report also that usage in jobs.
Okay. Is the setup public or?
No.
That is not public. Okay. Any plan of making it public? Well, they just said that they don't know yet if that's gonna be made public. That would be a question for Guillermo, but Guillermo said that it's above his pay grade. And related to that as well, do you have an idea of what is the size of the data you have gathered with Xalt? Yeah, wait. 60 gigabytes of data every. Okay. Every 3 months, 60 gigabytes. Okay, and I assume that's already heavily tuned and filtered. Okay. Okay, thanks.
More question?
One question about regression testing that you did. What do you actually test exactly?
So it's for testing from scratch the build of our software stack. So in general, when you build, EasyBuild downloads the package and then start building. So for instance, sometimes links gets outdated and you want to test that from scratch. And then also we have continuously updates on the either operating system or on the programming environment that does change a little bit the environment, so some build might fail. So if the module is already present in our production build, does not rebuild that, because by default EasyBuild does not override a build. So the regression will override everything, so in a separate folder, of course. And then to ensure that if you want to rebuild now the software, then you are able to do that with the current recipe that we have in our repository. So that's...
Thanks.